You can do it only by one independently, but usually it's done by applying both actuators. So control allocation in this particular application can ensure that you get a desired combination of your actuators, that is the elevators and the ailerons. So in this work, specifically I'm using the retrospective cost adaptive control algorithm to constrain the control input to a desired subspace, and I'll make that idea a little bit more clear. So there's this survey paper actually gives a very broad overview of where we control, broad overview of the control allocation research. And basically, the problem they are trying to solve there is that they consider a system where the input is actually tau. So that's the actual input that you need in the system. But then you have many actuators that can affect that input, so that the actual input to the system tau is affected by a lot of actuators u. And in the linear case, this function g of u would just be b of u. So the problem is that you have a system which is driven by tau, but this tau is given by some sort of combination of these input u. Now, if you have, so u is p-dimensional and tau is n-dimensional. So if you have more of u's than tau, that is p is greater than m, in that case we just call the system to be over-actuated. And usually in this case, in over-actuated systems, if in over-actuated systems, u that satisfies this condition is usually not unique. So you have a lot of options of how to allocate these u's. And the problem is to allocate the u's in an efficient way. So control allocation problem is usually concerned with minimizing some sort of cost function, some sort of combination of some norm of these control actuations u. But in this case, our approach is focusing on constraining this u to some chosen subspace of Rp. For example, let's say, let's give a sign. No. So we consider this basic feedback loop with an adaptive controller, where the dynamics is given by some map f and g, and the inputs are, so this input is in the p-dimensional space. The problem is that to develop an output feedback control u of k, control law for u of k, such that this input u is constrained in some subspace. For example, if you had two controllers, but you don't want these controllers to be these two control actuators to just go anywhere, but you want to constrain these two actuation inputs to this subspace, then that's the problem. You choose the subspace n, the subspace defined by the matrix n as the range space of the matrix n, and then the control should stay inside that subspace. That's the problem. So for example, in a linear system, if you had an over-actuated linear system, at steady state, the outputs and inputs are usually given by, you can write the steady state output as this expression, where u usually is not going to be unique. And this matrix ends up being wide. So if you have a wide matrix, there are many solutions to this problem. So in two-dimensional case, if you want a constant value of y, there are many values of u1 and u2 which would actually satisfy that value of y. So any solution on that line gives you a constant value of y. So you can choose any value of u1 and u2. And the problem is to construct a control law such that u1 and u2 are always given in a specific ratio. So the controller that we use, this controller that we use in our work is given by a time series model where pi's and qi's are the coefficients of the controller, and uk minus I and ck minus I, they contain the past measurements. That's the past inputs, these are past measurements. These past measurements could include the reference command, they could include the output error, they could include the actual outputs of the system. All of these things are measured. Now this time series model, I can write this as phi times theta, where phi, the regressor matrix, contains all the past values of the measurements, inputs and the measurements, and theta contains all the coefficients that I'm going to basically optimize to give me this controller. Now, this is just a little bit of algebra of how to construct phi using the past data. RCAC, like I said, we use retrospective cost adaptive control algorithm to update in this work, and that's what we use to update these controller coefficients. And here's the algorithm that RCAC uses. So we define this retrospective performance variable, z hat, using the measured errors and the constructed regression matrix and past inputs. This signal is passed through this filter, where this filter, which is the target model, and the interpretation of target model is actually very nicely shown in this paper. This filter is given by this FIR model. So this is just these, we choose these coefficient matrices. And these coefficient matrices are the matrices which are going to define the subspace to which the input is going to be constrained. So this is just an FIR model with these coefficients Ni, and we construct this, we define this retrospective cost function, which is basically a quadratic convex function in theta hat. So z hat is, so this is like z hat square, and that's phi theta square. So all these terms have theta squares, theta, and a constant. So that's basically a quadratic convex function. It's very easy to minimize. We use RLS to minimize this cost function. And the minimizer of this cost function, which is given by, which is shown in here, is what is used as the controller coefficient at the next step. So we set the control input at the next step as the data that we just had, and these optimized controller coefficients, which is the minimizer of this cost function. Now, like I said, this paper actually goes in a lot of detail about multiple interpretation of this filter GF, but I'm going to use a slightly different interpretation of this filter GF. So once you choose this filter GF, we can do some algebra, and we can write the control input, which was this guy, as actually this guy. So that's a matrix times a lot of data. Now this is only for analysis. That's not how the control input is computed, but this is what you can, when you write down the equations, you can express the control output as this. So the key thing to know here is that this control input is going to be in the range space of this matrix, because it's this matrix times something. And when this matrix times something is always going to be in the range space of this matrix. So that's the key. This is the key property that we exploit to constrain the input to any desired subspace that we want. Yeah, that's what it says. The control is constrained to the subspace of basically this matrix. So you choose this matrix, and the control is guaranteed to be in this subspace, because that's how it is being computed. So let me show you some examples. So we have a linear system that I just constructed randomly, and know that this has same columns in the B matrix, so the controls are actually co-located. It's the same. So we assume that we have two exactly same controllers, but we want to assign different control inputs to each of these two channels. So all we do is set the desired numbers in the filter. So this is N1, I'm only using one filter coefficient here. And this shows the output. So I ask the controller to drive the system output to a steady constant value. It produces two inputs, which are in the given ratio. I set it to be 0.5 and 1. So one is going to be twice the other. And that's what that shows. And these are the control coefficients that they converge to something. Similarly, if we had two independent actuators, which can be seen from this construction of the matrix B, which has two different columns. So we have two independent actuators. These are not in the same direction. In that case, also, you can assign any ratio of the control actuators U1 and U2 that you desire. So in this case, I set them to be 0.5 and 1. So again, it's going to, the control output is, one of them is twice the other. And you can see that U1 and U2 in that picture are also, so this one is converging to 0.2, that one is converging to 0.4. Last example, these are just numerical examples that I constructed to demonstrate the idea. We choose each channel such that each of these channels independently do not give a fully controllable realization, but simultaneously they give the fully controllable realization. And in that case also exactly the same thing happens. U1 and U2 that the algorithm is computing, they are always in the fixed ratio given by the choice of the filter, GF, or the coefficient N1. Okay, to a more interesting application, we apply the same idea to the lateral flight control of the NASA GTM model. So GTM model, it's a lot more complicated model. It's not a simple model of flight dynamics. It includes all the aerodynamic effects. It has a lot of trim function, and it has interfaces for feedback control from realistic sensors. Our goal in this problem is to achieve horizontal circular flying with the desired aileron and rudder effect. Like I said, aileron and rudder can be used simultaneously to turn the aircraft. So the aircraft is going straight, and we want to, so from that trim condition, we want to make it go in a circular, horizontal circular flight. So from one trim condition to another trim condition. So this is the GTM setup that we use. A lot of details of this model are actually given in this paper. The performance variable is basically the turn command, so the actual turn rate of the aircraft and the commanded turn rate of the aircraft. So I want it to turn at a certain rate, it's turning at some other rate. The difference is the error. That's the error that I'm going to minimize. The control inputs that we use are the aileron and the rudder. And the controller that I'm going to optimize is going to be driven by the turn command. So that's like the feed forward part. The performance variable, that's this part. And then another signal, which is the side slip angle, because all these signals are available from the sensors. So we assume that the aircraft is initially in a straight line. So forward velocity is constant. All other angle rates are 0. We ask the aircraft to go to another trim where the turn rate is constant at 5 degrees per second. So it's basically always turning in a circle. And then we set the filter coefficients to be 1, 1, in the ratio 1:1. So that means the aileron and the rudder are going to be used in the same ratio. So the control, if the control energy, in a sense, which is being requested out of the aileron and the rudder is exactly the same. So this shows the rudder and the aileron responses. So there's an initial transient, and then finally it converges to the value where it needs to converge. And both of these are always in the ratio 1:1. Now blue shows the actual, and the red shows so blue shows what we request, and since there is actually aerodynamics, there's going to be slightly different values that are applied to the actual aircraft. So reds show, no, I said it backwards. Red are the requested, and the blue are the actuals. And this one shows the turn rate. So initially we are going in a straight line, so there is no turn, and after a slight transient, the turn rate starts increasing and then converges to the requested value of 5. The controller coefficients converge, and this plot shows the U1 and U2, which is the aileron and the rudder effect. They are in the ratio 1:1. Now, if you wanted to use slightly different ratio of the aileron and rudders, all we have to do is set up these numbers slightly differently, and we see we get the same response, similar response, not the same response, but with a slightly different combination of the aileron and rudder based on our choice of the filter coefficients. So that is how, this is basically using the, I don't want to say a flaw, but a structure in the RCAC computation. So that is it. So we presented a slightly different approach to a control allocation problem where our goal is to essentially constrain the output, control input to a desired subspace. And it is based on the fact that the control input in RCAC is constrained to the range of the target model coefficients. All the numerical examples that I considered and the flight example, they are both minimum phase. The non-minimum phase plans actually require the non-minimum phase 0 information, which means I have to use multiple filter coefficients, and I didn't do that yet, so that's the part that we are going to focus in the future. And that is it. Thank you so much for listening.
So, thank you. Questions?
Yes.
Are the results you get in some kind of
then on the minimization of this cost function. So we're not minimizing, we're not saying that this is necessarily going to minimize energy, but by choosing the values of RZ, RU, and beta, we can get different responses. So it's not minimizing energy, it's basically minimizing this cost function.
Especially in the, for a flight, in the better to choose the inputs that the output, or that you use minimum amount of energy.
Right, that is correct, but we are just saying that in this particular problem, we have this method where we can assign control. So my goal is not to turn the aircraft in the most energy efficient ways, but the goal is to turn it with a specified usage of the actuators. For example, if you have one actuator which is really, really old and one actuator which is really, really new, and you want to somehow change the ratio in which they are used to somehow match their maintenance cycle. So in that case, you may want to do such a thing. Yes.
Yeah, I guess this is one of the difference between the different disciplines. In chemical process, we dream to have more actuators.
Yeah.
Normally we have fewer actuators than output to control. So, but in chemical process anyway, so if we have any freedom for the actuator, we normally will do some optimization. So as put this as the
So,
or make the aircraft more stable or more comfortable. So do you consider to use this actual degree freedom to do some optimization to make some additional use?
yeah, we haven't so far, but yeah, definitely that could be like we can have an auxiliary cost function, and then or maybe add to this cost function to include those effects. So this minimizes both and physical objective like minimize the energy or some other factor, and at the same time producing the control inputs into a desired substrate. So we haven't done that, but definitely that's a good point, and we should include. We can definitely try to include those types of cost function in this equation. The key simplicity here by using this expression is that this ends up being a quadratic convex function. So this computation is really simple. Now if I include like dynamics to minimize, so if I have to include the energy, I have to include the whole dynamics, right? And then the solution might not look as simple.
But normally do in the static form, so with two layers. The top layer you do the static optimization. Then send the set form.
Right. So if we can do that two-layer control, like a higher level controller will do one thing and the lower level controller will do the other thing. That can be done. Yeah.
To be honest, rethink the example because as somebody with a pilot license, the synchronization between rudder and rudder is very defined because of if you fly a curve, then you have to keep the vector of the gravitational center force always
Right.
control.
Right.
And that means you have an exact synchronization constraint.
Yeah. Because I don't fly. That's why I did not know that problem. But are you saying that they need to be in a synchronization?
They need to be, and that has something to do with energy efficiency. Yeah. And if you go away from that fixed relation, then you have you do that sometimes. If you have a deep descent, for example, you slip to reduce speed. That means it has to have something to do with not energy efficiency.
Okay.
And that is the reason why a proper curve is always.
But that would be a good application for this, right? Because this control input is guaranteed to be in some synchronized ratio. If you give me a ratio, this control input is definitely going to be in that ratio.
That's correct. Yeah. You can tune that in a way that.
Yes. Oh yeah, we didn't use that tuning argument, but that's a good guide how you can choose these ratios.
Okay.
Yeah.
Any
Thank you so
further
much.
questions? No? Then? Yeah. Be fast.
So because you constrain your input to some sub-region, so does this constraint include saturation constraint?
No. That's the saturation would usually typically be applied after the computation. We haven't done. I haven't done many examples, but I have had I've done a couple of examples where just numerically in linear system, that I saturate one of the actuators. And obviously it's going to degrade the performance, but nothing catastrophic happens. It still works. The computed output is always going to lie in the range space of whatever matrix you choose.
Okay,
Yeah.
thank you very much.